Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Sridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our subject Basic Electrical Engineering in topic Magnetism, we'll understand magnetizing curve of ferromagnetic material and understand the relationship between magnetic induction or magnetic field flux density and magnetic field intensity or B and H relation. And in the process, we'll also understand for ferromagnetic material what is absolute permeability and relative permeability and how it varies with variation of applied magnetic field. Let's start study of magnetizing curve for ferromagnetic material. The variation of magnetic induction in air and iron material with respect to applied magnetic field is shown here. Now this relation of magnetic field flux density or magnetic induction with respect to applied magnetic field intensity is known as magnetizing curve. Since the permeability of iron is very high compared to permeability of air, so for same applied magnetic field intensity, the value of magnetic induction in iron is around 1000 times more than that of air. So in this scale of magnetic induction, the values are in Tesla if we study magnetizing relation of iron material, and the same value shown here in this scale are in millitesla, 1000 times less for air. The magnitude of air permeability is small as well as constant. So for a particular value of applied magnetic field intensity, an ampere per meter, the magnitude of magnetic induction in air is in millitesla, and with increase of magnetic field, magnetic induction also increases in a linear straight manner with uniform slope, and this slope of BH relationship represent constant and small value of magnetic permeability. But for iron, the variation of magnetic induction with variation of magnetic field intensity is not a linear function, and magnetizing characteristic or BH characteristic of iron is a curved relationship where the value of magnetic induction for same amount of applied field intensity is around 1000 times more than that of air. But the rate of change of magnetic induction with magnetic field intensity won't remain same, and it varies and decreases with increase of applied magnetic field. When applied magnetic field is increased from a very small value, for initial small amount of increase in applied magnetic field, the increase of magnetic induction in ferromagnetic material is almost linear with a very high and constant slope. But this slope of BH characteristic as shown by blue arrow, which is initially high and constant, gradually decreases as applied magnetic field increases onwards. In this non-linear region, the slope of magnetic induction in iron material and applied magnetic field intensity curve goes on decreasing, and finally in saturation condition the slope of this magnetizing curve becomes almost zero. Now in this saturation condition, the value of magnetic induction in iron will not increase appreciably even with a tremendous increase in applied magnetic field intensity. A current carrying solenoid produces almost uniform magnetic induction in its core part, and a air core solenoid got a small amount of flux and flux density even with a high amount of current. And if air core solenoid is converted into a iron cored solenoid, then the amount of flux and flux density become much more even with smaller amount of magnetizing current, and this indicate higher value of magnetic permeability in iron core as compared to air core, and permeability of medium indicated by Greek letter mu denotes ease or readiness of core material to accept and allow the passage of magnetic flux through the core material. So in comparison to air core, flux can easily and with higher amount passes through iron core as shown here in this drawing. In the same applied magnetic field intensity in air and in iron core, the amount of flux density is different, and the reason for this difference is higher permeability of iron medium. The permeability of a medium is a measure for easiness or readiness for the flow of magnetic flux across this medium, we can say permeability of a magnetic material is just like electric conductivity of a conductor, which allow easy current flow in a higher conductivity material. Similarly, in a ferromagnetic material having high permeability, the magnetic current or magnetic flux can easily pass through these higher permeable ferromagnetic medium, and due to that, the amount of flux density, flux per unit normal cross section area, become 1000 times more than flux density in air for the same applied magnetic field intensity. In the same applied magnetic field intensity, the value of magnetic induction or magnetic flux density in iron core material B is much more than flux density or magnetic induction in air B naught, and the reason for this difference is difference in permeability of air and iron core material. But in any media, the value of magnetic flux density or magnetic induction is directly proportional to applied magnetic field intensity, and this proportional relation can be converted into equality using a constant, and that constant is known as permeability of that media in which we are finding out magnetic induction. Now the absolute permeability of any ferromagnetic material is represented as mu 0 mu r, where mu 0 is absolute permeability of air or vacuum. As far as magnetic properties is concerned, air is so tenuous, so diluted that its magnetic property and property of vacuum are treated just identical, and permeability of air or vacuum mu naught is universal constant, and its value is equal to 4 pi into 10 to the power minus 7 in Henry per meter unit. And absolute permeability of any ferromagnetic material, mu is represented as permeability of air multiplied by mu r, where mu r is relative permeability of ferromagnetic material with respect to air. And if we rewrite this relation of magnetic induction in terms of applied magnetic field intensity mu 0 mu r h as mu r times mu 0 h, then this mu 0 h becomes magnetic induction in air, and magnetic induction in iron core will become mu r times magnetic induction in air. And if mu r is say 5000, then magnetic induction in iron core material B will become 5000 times magnetic induction in air media. Relative permeability of any media is ratio of absolute permeability of that medium with permeability of air, and both absolute permeability of any media and permeability of air are measured in Henry per meter, and this ratio mu r become a number only without any dimension. And if we put different material in same magnetic field intensity H, then we'll find that different material got different value of magnetic induction in that medium, and this variation in magnetic induction in any media takes place due to variation in magnetic permeability of that media. And vast majority of material are either diamagnetic material or paramagnetic material, and in these materials magnetic induction in material medium is very close to magnetic induction in air, because permeability of these dia and paramagnetic material is very close to permeability of air, and relative permeability of diamagnetic material is slightly less than 1, and for paramagnetic material it is slightly more than 1, but for both dia and para relative permeability is very close to 1, and these material dia and para are known as non-magnetic material. And typical example of non-magnetic material are all three good conductor: copper, aluminum, gold, platinum, manganese, magnesium, water, wood, oxygen. All are either dia or paramagnetic material, and their magnetic properties are very close to that of air. But in ferromagnetic material, the magnetic induction in material medium become much more than magnetic induction in air for the same amount of applied magnetic field intensity, because these ferromagnetic material got a very high value of relative permeability. And typical ferromagnetic material are metal like iron, nickel or cobalt, or alloys formed by these three iron, nickel or cobalt metals. And this class of material got higher value of relative permeability, got engineering importance, and we also call them as magnetic materials. Metals such as iron, nickel, cobalt, or alloy of iron and carbon steel, and other alloys of iron, nickel or cobalt are known as ferromagnetic material. And in these ferromagnetic material, for same amount of applied magnetic field intensity, the magnetic induction or flux density become much more than flux density in air. And the reason for this increased value of magnetic induction in these material is relatively higher value of relative permeability in these ferromagnetic material, which have relative permeability ranging from few hundred to few thousands or even greater. And in ferromagnetic material, magnetic induction becomes mu h, where mu is mu 0 times mu r, and magnetic induction will become mu r times magnetic induction in air. So for same amount of applied magnetic field intensity, the straight linear magnetizing BH relationship of air passing through origin indicate that permeability of air is constant and it will not change with change in applied magnetic field intensity or working magnetic induction value. And smaller value of magnetic induction in air compared to magnetic induction in iron for same amount of applied magnetic field intensity indicate smaller value of permeability of air as compared to permeability of iron. Whereas in magnetizing characteristic of iron material, the magnetizing relation B and H curve of iron is not a linear characteristic that represent variation in permeability of ferromagnetic material when applied magnetic field intensity or working magnetic induction value is changed. So permeability of air is universally constant and will not change with change of B or H, whereas permeability of iron, though high in magnitude and produce higher amount of magnetic induction for same amount of applied magnetic field intensity, but the permeability is not constant and it will change with change in value of H or B. This black curved magnetizing characteristic or magnetic induction and applied magnetic field intensity relationship of ferromagnetic material is explained by Weber domain theory of magnetization. All ferromagnetic material atoms possess inherent magnetic dipole moment or magnetic property due to unpaired spinning electron in their atomic configuration. And more significant fact is, according to Weber, these ferromagnetic material have domain structure. Now in magnetic domain structure, a small volume, roughly order of 10 to the minus 10 meter cube, have huge amount of atoms, and all those atoms of a single domain volume form a strong cooperative association and align their magnetic dipole moment in one direction only and become a relatively powerful magnetic dipole moment. Individual atom got a magnetic dipole moment of the order of 10 to the minus 23 ampere meter square, and when such huge number of a domain volume form a cooperative association, a domain become a relatively powerful magnetic dipole moment. And in unmagnetized virgin ferromagnetic material, all these domain of entire volume got different random oriented positions, and resultant vector summation of all those magnetic dipole moment is 0, and material got 0 magnetic induction for 0 applied magnetic field. And when applied magnetic field strength is increased, initially there exists a linear increase in magnetic induction with a high and uniform slope. And the reason for this increase of magnetic induction in ferromagnetic material is tilt of magnetic domain in the direction of applied magnetic field. If applied magnetic field is in red arrow direction, then a domain having slight angle deviation with applied magnetic field, which is easy to rotate, get tilted by a slight increase in applied magnetic field, and due to that ferromagnetic material generate its inherent magnetization and induced magnetic induction, and that enhance magnetic field flux density in this material. And further increase in magnetic field intensity will further tilt a domain in the direction of applied magnetic field, and likewise tilting of domains in ferromagnetic material generate induced magnetic induction in ferromagnetic material, and a high and uniform rate of increase in magnetic induction takes place with increase of magnetic field intensity, and that represent a higher value of dynamic permeability in this initial linear region of ferromagnetic material where domain tilt is taking place with increase of magnetic field intensity. When ferromagnetic material is placed in magnetic field and applied magnetic field is increased, first easy domain having small angle orientation of magnetic dipole moment get aligned with applied field first, and then gradual increase of applied magnetic field, continuously aligned domains with greater angle with applied field, and soon majority of domain get aligned with applied field and only difficult domain having 90 degree or so angle with applied field left to be aligned. And now the slope of increase in magnetic induction with increase of applied field decreases, and that represent continuous decrease in magnetic permeability of ferromagnetic material. And this is so because now to tilt these difficult domain it demand higher amount of increase in applied field and lesser increase in resultant magnetic dipole moment or internal induced magnetic induction or resultant magnetic field flux density in material. So this slope of BH relationship keep on decreasing, results in decrease in value of dynamic permeability, as slope of BH characteristic is the permeability of material. Due to presence of domains in ferromagnetic material, the shape of magnetizing curve or relationship of magnetic induction and applied magnetic field becomes similar to the leg of a sitting person, and between ankle and knee increase of H results in linear and high rate of increase in magnetic induction, but after knee point the initial linear constant and high rate of change start decreasing, and slope of magnetizing characteristic during tilt of difficult domain continuously decreases, and this indicate saturation condition of magnetic material. And in that saturation condition, increase of applied magnetic field intensity won't result in appreciable increase in magnetic induction in ferromagnetic material. When external applied magnetic field intensity is increased, the first tilting of the easiest domain will take place in the direction of applied field after ankle point, and further increase of external applied field continuously aligned and tilt more and more domain, and this partial magnetization of ferromagnetic material continuously increase internal magnetic dipole moment or induced magnetic induction or magnetic flux density with increase in external applied field up to knee point with constant and high rate, and we got linear highest sloped B and H relation between ankle and knee. And after knee, first difficult domain get tilted, require higher amount of increase in external magnetic field and lesser increase in magnetic field flux density, and after deep saturation condition, when almost all internal magnetic dipole moment get aligned with external magnetic field, the further increase of external applied field can't increase magnetic dipole moment in ferromagnetic material or induced magnetic induction in ferromagnetic material, and when in deep saturation condition the whole material become a single magnetic domain, the further increase in magnetic flux density saturate and dynamic permeability becomes only permeability of air, as no more induced magnetic induction is possible after saturation point. Between ankle and knee point in the initial linear part of magnetizing characteristic, the absolute permeability or relative permeability of ferromagnetic material is high and constant, as increase of applied magnetic field intensity results in significant increase in magnetic flux density, but after knee point, as slope of BH characteristic decreases, absolute permeability and relative permeability of ferromagnetic material continuously decreases in a non-linear characteristic part, and it become minimum equal to permeability of air, and dynamic relative permeability become just 1 in deep saturation condition. Since in this non-linear portion permeability is not constant, so when we use magnetic material we must consider this variable nature of permeability in this non-linear characteristic part. We never use materials in deep saturation condition. For optimum performance we use magnetic material just near knee position, so that least amount of applied magnetic field intensity or magnetizing current produce maximum amount of magnetic induction or working flux in our magnetic circuits. This numerical example will explain the role of higher permeability of iron material in magnetic circuit design. In a solenoid, the core has a radius of 1 centimeter. Now this is used to find out cross-section area of magnetic circuit. Now the length of solenoid is 0.4 meter. We have to find out resultant magnetic flux in the core when this solenoid has 200 turns and magnetizing current is 0.5 ampere. Now in one case, the core material in which flux is produced is air only, and in second case we have used a iron core in solenoid with relative permeability 1500. So in air core condition, the permeability of medium is permeability of air, and that is constant 4 pi into 10 to the power minus 7 Henry per meter. We know the working flux is product of flux density and normal cross section area, and flux density is mu0 times H, and for a solenoid, product of number of turns and current is called mmf, and mmf per unit length become applied magnetic field intensity, and mu0 times H become magnetic induction, and magnetic induction multiplied by normal cross section area become working flux. Now the value of mu0, permeability of air is 4 pi into 10 to the power minus 7, number of turns in solenoid is 200, magnetizing current is 0.5 ampere, and the length of solenoid is given 0.4 meter. Now the cross section area is pi r square, so it is pi and radius 1 centimeter in meter is 0.01 meter, and it is squared and multiplied with pi to get cross section area. And when this mathematical relation is solved, we got that resultant flux is very small. It is of the order of 10 to the power minus 7 Weber or 0.1 micro Weber. So in air core solenoid, when permeability is small, appreciable amount of mmf, good number of turns, and appreciable amount of current won't produce significant amount of flux. But in iron core, the permeability of media become mu r times mu naught. Mu naught is 4 pi into 10 to the power minus 7, and relative permeability is 1500. So permeability become 1500 times more than that of air in Henry per meter unit. Now the same relation of flux is magnetic induction multiplied by normal cross section area, and magnetic induction is mu0 times H, and H is independent of medium. It is mmf per unit length, and mu is mu0 mu r. Now in place of mu0, mu r, number of turns, magnetizing current, length of solenoid, and cross section area of solenoid, when numeric values are placed and solved, we got that magnetic flux now become 1500 times more than that of in air condition, and it is appreciable amount of flux 1.48 into 10 to the power minus 4 Weber. We hope this interesting and informative video has explained magnetizing curve of ferromagnetic material, and now you could understand when applied magnetic field intensity is increased, first tilting of easy domain take place, then during tilting of difficult domain, slope of BH relation decreases, that results in decrease in dynamic permeability or relative permeability, and after deep saturation, magnetic induction become almost constant even with increase of applied magnetic field intensity. This is very useful learning video. Do share it with your friends. If you can spare more time, do visit other playlist of this channel to enhance your electrical engineering knowledge and capabilities. Happy learning. Have nice time. Thank you very much.